Our next presenter, to use an analogy with what Dave said at the end, our next presenter is an experienced person, a person who has a good experience, but it's also someone who is at the end of his career somewhat, but he demonstrated flexibility despite his age, which is not based on his biological age. So his name is Michel Belleau. Michel was one of the first with Resolute Forest Products in their first acquisition, data acquisition of 12,000 square kilometers. So Michel Belleau, through the Resolute Forest Products company, collaborated with the project. He brought new ideas. He had new insights and comments about optimization. So that demonstrates his openness and his creativity in these files. Michel is superintendent at Resolute Forest Products and has been working since 1989 to this date for PFR, for Resolute. Since 2006, he's superintendent for operational planning and forest inventory. So I'd like to invite Michel to make his presentation. That's your pointer here. Good morning, everyone. I'm not a specialist of presenting, but I'll try to explain to you a little bit what we're doing with LiDAR in the Lac-Saint-Jean region, what we've been doing now since some time now. My presentation plan is our first steps. We had to learn to walk first. We were not specialists, but we saw an opportunity for forest operations with the LiDAR. First, experiments, and after that, ongoing projects and future perspective and outlook on the future. In terms of the first steps, we had a terrain digital model with shaded relief. That's the basic thing we used. We saw that it was really useful for roads. Allows us to pre-validate road routes that were planned and make the first corrections, and creates also a slope layer to visualize the breaks and the steep slopes so as to identify the non-harvested regions. At the beginning, we received a plan from the department. Can we exclude certain zones which we know that operationally will be difficult to exploit? That's what we did. We could justify the non-harvesting through the position of the slopes. Another thing we did is to create links between the results of the fine interpretation of airborne photographs and LiDAR data. We've been working since 1997 with fine photographs to identify the precise volume per hectare per species and per diameter per stem. That's something we had developed cubic decimeters per shaft, per species, per stand. We wanted to do the same thing with the LiDAR, to better assess the volumes and appraise their values and plan for the supply of plants. We have 5 sawmills in our area. Some are specialized in 2x4, some others are specialized in Roundup 2x8. So we could identify which sectors could supply the best plant. When we created our polygon, we had to develop which plant this polygon would supply. We wondered if the LiDAR could not help us do the same thing as the fine photographs. With the first experimentation, the first thing we did is to validate the pre-planned routes for construction roads. We had selected a sector for which we had made the planning in a conventional way with air photographs and mapping and orthophoto mosaic. We did a validation and route modification of the roads using LiDAR data. We validated this finally with the actual building on the field. So we did conventional first, then with LiDAR, and we validated this with actual results in the field. What you see here is the first planning that was done. You can see that this is a planning that was done when we had road credits, where you see a lot of purple, where you see a lot of loops and forks that had been done in that context at the time. It gave us 31.3 kilometers of roads in that way. We knew very well that we had to be careful with that when we compare things. It's not because we had planned for 31.3 that we'll end up a lot lower. If we had no LiDAR, we would not necessarily have reduced the number of kilometers of roads. It might have gone down, but it's the terrain that commands what happens actually. That's just the basic planning. After that, we did a new planning exercise using LiDAR this time. We took the same area, and at that time, we came up to really specify exactly where the routes should be for the roads so that it's optimum. We lowered the number of kilometers. We moved from 31 to 26.7 kilometers of roads. Finally, we compared this with what actually was built in the field. We constructed a lot fewer kilometers. There was supposed to be a road there. We didn't do that because we asked the carrier to do the transportation further, and we compensated that with the cost of the transporter because he had no material to build a road in that area. Instead of going large distances to transport material, we preferred to compensate. It's the kind of practical things. The LiDAR will not necessarily make the final decision. It's the situation on the ground that will finally be the most important thing. But what we improve a lot is the initial positioning. The walking by 4 men is reduced by a lot if we use that product. Then the slope form files, creating form files for the GPS and the forest equipment transporter, and that's another project we worked on. That form file presents polygons with slopes of 30% and 45% and more. Why? Well, because those are hurdles to the circulation of machines. The idea here is to finally come up with, it's a tool that is very much appreciated by operators and allows us to identify very quickly the obstacles due to slopes and breaks, and allows us to predict the journey in the harvesting polygons. There was a lot of waste of time due to the fact that people were connected and wanted to go through a place where they couldn't go through. They had to come back and change the route. Visualizing ahead of time where we can go through is a huge savings for operators. And so what we did, we created layers of slopes from 30 to 45 and 45 and more. And what it gives you is this here. You see what we're doing. We create polygons, slope polygons, the shaded areas being those 30 to 45% and 45% and more in red. What do we do with that? We put that in the tree feller GPS systems. And so what this does is that we create an IMG point, and the tree feller operator can see in his block that they can't go through that way. The place to go through is here if they want to harvest. But if they don't want to, they just know that they have to go there. They know where the slopes are. So that allow operators, before they harvest, when you are in front of a forest that is 15 to 20 meters high, you don't see the ground. That allows them to see the ground ahead of time. Once the operators have tasted that, you can't take it away from them. They're going to hang you, that's for sure. Now, in terms of ongoing projects, we have a project to improve the predictability of supply, to deliver to the plants. In terms of volumes per species and cubic decimeters per stem, we have a project that's ongoing. We thank very much Dave, who's supporting with that project. We want to link the LiDAR data in terms of cubic decimeters per stem and the volume per species coming from the AIPF mapping. One of the big questions I had with LiDARs is, well, LiDAR seems to be good for diameters, for heights, but species, I don't have the species. And for us, knowing how many furs we will come in, at what time of the year we will enter all those fir trees, and taking the time for the new dryers from August to September, how many gray pine or black spruce stems will we get in? For us, for the industry, it's very important. The species are very important. We're trying to ally our LiDAR data with the AIPF data, airborne, and we did a project in 2015 for the 2015-2016 for 2 work sites. There's a site in the south where a mixed deciduous environment. I wanted to see if it works also for deciduous or mixed, and we have a second project more to the north. If we look at the results, we compared the volumes of inventories that we had before compared to the total volumes detected by LiDAR plus AIPF. And we can see that there's quite a good difference in terms of volume per species here. I don't know what happened exactly, but you can see that there's quite a difference. That's the 511 hectares that were used to do this analysis. Then we compared with what we actually harvested. We estimated the wooded material. What would remain to be added is the crown part. We could have added that there. The crown part that we don't process, which is not measured, but it gives us the forest biomass at least. We could have measured also that crown volume to check if that would make it closer to the LiDAR analysis. The gap, the difference, allows us to see. Here I show the differences in the inventories. We had significant differences, really important differences in terms of the third inventory. And if we bring it back on a comparable basis with the LiDAR data, we could see that overall we're getting better. We still have important differences in deciduous, but if I had added the crowns to that, I would have reduced that gap, which wasn't done. The first observations show an improvement of results for the total volume and SCPM volumes if we add up the data coming from the LiDAR and the AIPF. Volumes per species remain variable, but the gaps are lower overall. In mixed forests, there's still some adjustments to be made, but if I compare what we had before with what we have today, there's a good improvement. What is more interesting in my case, because we cut a lot of softwood surfaces, is analysis in softwood environments. Once again, the third one and the LiDAR, we see that the third had overestimated volumes compared to what we had through AIPF and LiDAR. And what we have here is what we actually harvested. So you can see that here we just improved quite a lot. I was very surprised with those results. I wasn't expecting that. Maybe it's happened by chance. We'll continue with other sectors, but it looks promising. The differences on the third decade are here, and if we have this one with the LiDAR data, listen, it's within 1% precision on the total volume that was simulated by Dave compared to what we actually harvested. Only 1% difference. We estimated forest biomass at 2% in the case of softwood, and that's approximately what we have annually. So we want to continue the experiment. We'll take other sectors that were done by other tools on the territory, and we'll continue to test. But at first sight, at first glance, it looks very interesting. So that we want to have the product. We're demanding the product. Ongoing projects, there's a brand new project to reduce the layering in the riparian areas. People are doing more team coaching now. We're talking about quality, health and safety, and so on. And we have less and less time to putting ribbons on the ground, the ribboning. Do we have tools that would allow us to do this? And our goal is to create from the LiDAR data the boundaries of the riparian ecotones for lakes and permanent rivers, validate the contours on air photographs to do the necessary adjustments for the ecotones, and create a buffer area of 20 meters from the ecotone contours in the riparian areas to specify the boundaries where the machinery is not supposed to circulate or where they're not supposed to harvest. With the LiDAR data, we came up in red with the forest of less than 2 meters in height. It's the less than 2 meter high vegetation on the borders of the body of water. All this area, that's the non-harvesting area. If someone had walked on foot to put ribbons on the ground, they would have started from there. So based on the LiDAR data, can we align this with orthophotographs? Can we save that portion of ribboning? And so we validated with orthophotography. We could see that we were not wrong to give exactly, the LiDAR gave us exactly what it was supposed to be. And what we did here, the contour in pink, which you see there, is the contour that we'll include in the GPS of the felling machine. And what's in shaded is what we would have done conventionally. We would have taken the creek with a 20-meter buffer. We would have taken the lake with a 20-meter buffer. But on the ground, it would have been the pink area, if you get it. So the shaded area is the actual part that we would have done using conventional methods. What do we do with that? The form files for the buffer areas will be integrated into the GPS of the harvesting equipment, and the integrated navigation system will be integrated in the GPS to visualize the non-harvesting areas. A visual proximity alarm and sound alarm will be integrated in the navigation tool. We developed an alarm as soon as the tree felling machine moves ahead. When it comes close to constricted and constrained area, automatically there will be a sound and visual alarm that will be shown to the operator to tell them that they're getting into the critical zone. You've got to start becoming careful. And the proximity alarm takes into account the different types of equipment. If we have a boom that works at 8 meters, the alarm will sound at 8 meters. If we have a felling machine that works at 6 meters, the alarm will be set at 6 meters. So that's what we have in place right now. The first harvesting blocks, which we are going to do in that project, we just started yesterday, the harvesting with that new method. We put ribbons on the blocks. We're not going with our eyes closed. We're not going through it blindly. We want this to work. We want to give it a chance to work. And we have a lot of assistance by the 2 management units in which we started that project. But our goal this year is to harvest 400,000 cubic meters with that method. So it's a major project. Another future perspective is to generate a permanent water body layer intermittently or permanently from the LiDAR data. We want to generate from the digital terrain model a layer of lines presenting the possible water flow. We want to classify these water flow lines because several lines are generated by the model. What you see here basically is the model that generated all the possible flows in yellow, and that is the network as it's shown on the map. And as you can see, it generates a lot of potential of possible streams and creeks. Now there's a classification that's necessary to make sure that the ones we take into consideration are the right ones. So in terms of water courses, validating the location of water bodies using LiDAR data. Here, what we did is that we sent people put ribbons this spring. The ribbons were put before we had the LiDAR, and they put ribbons on in the field. The black contours, the black lines are the creeks, and they're ribboned all along the water stream. The purple contour was what the LiDAR gave us compared to the blue one, which was what was done through mapping on the map. With the LiDAR, we improved a lot the positioning of the water body. Of the stream. If we had that contour, we're sure, and if we're sure this is the right one, we'll include that in the tree felling machine. We wouldn't have to put ribbons. We could simply put that directly into the tree felling machine and reduce the task of the harvesting supervisors. Now, validation of the positioning of water bodies, generate those and identify non-mapped streams with LiDAR. Very often on the ground, you find creeks or streams that are not on the maps. People put the ribbons in the spring before we analyzed with the LiDAR, and they had found an intermittent stream that had been ribboned. So what we can see is that the LiDAR generated that non-existent stream, and people had put ribbons on it already for protection on the ground. So what remains to be classified, there's a lot of work to be done there. I don't think we'll go just with that blindly with our eyes closed tomorrow morning. There's a lot of validation to be done because the LiDAR system generates a lot of streams and water flows. But if people participate, we could come to something really interesting. What we're doing right now is based on the intermittent creeks that are generated by the model. We send the foreman just walk. No, don't put ribbons. Now we ribbon 8 meters on each side. We could avoid that ribboning process. We would just send a foreman to walk. We'd take the track log of the GPS of the foreman that walked on the ground, and we generate the 8-meter buffer on each side. We put that in the machine's GPS, and we could avoid putting all the ribbons we put on both sides of the stream. Those are really applications that are focused on forest operations. That's about what I had to say. I wanted to give you the objectives that we have in working on streams, determining their exact location of creeks and streams, and reduce the work of harvesting supervisors. Those are really the objectives we have in this work. I don't know if you have any questions. we have about 5 minutes for questions. What I could say before questions is that work is on contours, for example, around streams and preventing waste of time in putting ribbons. That's a project that would be interesting for a lot of people in the industry, whether it's deciduous or softwood. I don't think an industry will say, I believe in ribbons and I want to continue to put ribbons. It's really interesting and promising, I'm sure, for the industry. Yes. What type of GPS do you use in your felling machines? Are there the standard Garmin's or what? In the case of the ribbonless project, previously we were on 421, the Marine 421 GPS systems. That's what we have in all our equipment, the carriers as well as the tree fellers, because we had a project. We do our annual reports based on those GPS 421. In the case of the ribbonless project, we tried to use the onboard computers built in the forest equipment. Each forest equipment has an onboard computer. We had it developed with a stem forest system. We had them develop. There's an antenna. There's a high-quality GPS chip which we put in the machine, and then there's an antenna that gets a precision of 1.5 to 2 meters. That's the type of precision we have. And as we often say, the tool we had on the ground to ribbon those streams was a Garmin ground GPS with a precision of 2, 3, 4 meters, or even sometimes only 5 meters. We want to replace that Garmin GPS with a more precise GPS with a precision of 1 to 2 meters. The important thing is that in all those cases, the location of the antenna should be right in the middle of the machine and the right place. And what we realized is often we have operators that tend to play with the parameters and the settings and the configuration. That leads to a lot of problems. So what we're working on is to lock them in place, lock everything they could play with, and all that we want to be standard. Operators can no longer touch that. But right now with the onboard computers, those that don't have it, we put Windows tablets with the forest system, navigation system, and it works very, very well. Thank you. Yes? A microphone, please. The question is, how much does it cost for a GPS positioning system? That was the question? Well, okay, basically, if we talk about a tablet, an outside tablet, we're talking about a $1,000 cost with the navigation system. And the tablet, and if you add the antenna, it's $1,000. When you install this for an onboard navigation system, we're talking about $500. That's approximately what it costs. It's not very expensive for what we can save. Thank you. Thank you very much, Michel. My pleasure.